on our very first day of homework, we were identifying the I gave it away. The centripetal force acting on the satellite as it orbited the Earth. And since our centripetal force always points inward, we had determined that our centripetal force here was our force of gravity, or gravitational force. And that is going to be what we are looking at today. So on Earth, we normally use the equation force of gravity equals 9.8 times our mass. But today we're going to look to see what do we do to calculate our force of gravity when we are not on Earth and when we cannot use this equation. Okay. So that 9.8 times your mass is actually a much more simplified version of a more elaborate equation where our force of gravity is equal to a gravitational constant g times the mass of one object that we're looking at. So in this case, that could be our satellite, times the mass of the other object that is experiencing that force of gravity, which in this case could be the Earth, divided by the radius or the distance between their centers squared. Okay. So there's a lot going on in this equation. So let's delve into it a little bit. So when we look at g, that is going to be a constant value. Okay, and that is going to be the universal constant for gravity. And that value is always going to be 6.67 times 10 to the negative 11th. So whenever you see that capital G, you can always plug that value in. And that's going to have units of Newton meter squared per kilogram. Squared. Perfect. When we look at M1 and M2, these are the masses of the bodies that are experiencing the gravity. So masses of the two objects experiencing the force of gravity. Because something that is really cool and not a lot of us think about is when we say that you are attracted to the Earth because of gravity, the Earth is also attracted to you because of that same force of gravity. What it means is that all objects exert an attractive gravitational force on all other objects. So as you're sitting in your chair, you are exerting an attractive force of gravity on your chair, and your chair is exerting an attractive force of gravity on you. The person who's sitting near you in class, you guys are attracting each other with this mutual force of gravity. So it's kind of wild that everything around you, you are attracting it to yourself, and they're attracting them to you, or attracting you to them, because this gravity is mutually felt. The reason why we don't often feel that force of gravity or that pull towards the people in your class, you're not just going to get pulled towards your classmate, is because that gravitational constant and your individual masses are so small comparatively. Okay. Awesome. And then the last part of this is then our radius squared. And that radius, we're going to define that as the distance between the centers of our objects. Or it's the distance from center to center. Okay. The mass of the Earth into this equation, and it would give you the same force of gravity on Earth as if we did mass times 9.8. So it's actually pretty cool. All right, so let's go ahead and look at an example. Let's say we were looking at the Earth, and the moon, which we know orbits the Earth in a close to circular orbit. Okay. So again, as a reminder, everything just kind of naturally wants to move in a straight line. Okay, so our velocity vector is still tangent to that circle because without that centripetal force pointing inward, our moon would want to travel straight and would not continue in that circular path. But because we have that force of gravity pointing inward, we have that circular orbit. And what's really cool here is that the force of gravity felt between the moon and the Earth is the same. So the moon is being pulled towards the Earth just as strongly as the Earth is being pulled towards the moon. But the reason why only the moon moves is because it is so much less massive. All right. So let's say we actually wanted to find the force of gravity between the moon and the Earth. So a lot of times in these problems, they're going to have to give you some important values. So for instance, here, we'll need to know the mass of the Earth is equal to 5.97 times 10 to the 24th kilograms. The mass of the moon is equal to 7.4 times 10 to the 22nd kilograms. And the radius between the Earth and the moon, or the distance between their centers, is equal to 3.8 times 10 to the 8th. Okay? And that's going to be the distance between their centers. Okay? Because remember, we're looking at from center to center. So you know in your homework, they're not always going to give you the distance from center to center. You're going to need to do some addition with adding the individual radius of the Earth plus the distance between the Earth and the moon, and then the distance or the radius of the moon itself. Okay, so this problem's nice because it gives it to you, but you know in your homework, you're going to have to add those individual components to get the total distance from center to center. All right, so then to get our force of gravity, we're going to use our force of gravity equation. That's equal to that constant times the mass of our first object times the mass of our second object, all divided by radius squared. Okay. And remember that constant g is always 6.67 times 10 to the negative 11th. Okay. So we plug in what we know. Here you guys are going to have to really be careful with parentheses, particularly when dividing by that radius squared. Okay. But we plug in our value for g. M1, M2, it doesn't matter here which one you make the mass of the Earth or the mass of the moon, just as long as you include them both, because those are the two bodies that our force of gravity is going to be between. And what's really cool, I keep saying this, is that whatever force of gravity we calculate that the Earth is exerting on the moon has that same attractive force on the Earth. Then divided by our radius, 3.8 times 10 to the 8th squared. And yeah, just be careful when you put that in your calculator. Put that whole thing in parentheses, okay, before you square it. So when we plug that in our calculator, hopefully if we're able to plug it in, we should find that the force of gravity between the Earth and the moon is 2.1 times 10 to the 20th newtons. Okay, so the moon attracts the Earth with 2.1 times 10 to the 20th newtons, and the Earth attracts the moon with 2.1 times 10 to the 20th newtons as well. All right, let's say, we wanted to find the acceleration due to gravity on Mars. Okay, and all we're given is that the mass of Mars is equal to 6.4 times 10 to the 23rd kilograms, and the radius of Mars, so the distance from the center to the surface, is 3.4 times 10 to the 6 meters. All right, so in this problem, we want to find our acceleration. And in the last couple units, when we wanted to find our acceleration, the equation that has helped us has been F net is equal to ma. Okay, the net force equation. F net is equal to ma. All right, so here we're trying to find the acceleration due to gravity on Mars. So we kind of want to think, when is gravity the only force causing our acceleration? And we should know the answer to that is when an object is in free fall. Okay? So what we can think about is if we're standing on Mars and we drop a ball. When we drop the ball, the force of gravity is the only object pulling down on that ball towards the surface. So the force of gravity is going to be equal to our net force. Yeah, that force of gravity is the only force acting in the direction we are accelerating. So that is the only force causing our net force or causing our acceleration. Okay, so let's break this down a little bit. So we have this new equation for force of gravity. Remember, we can't use 9.8 m because we're not on Earth. So we're going to instead use our constant times the mass of our two objects. So we'll say the mass of Mars. And in this case, the mass of the ball we're dropping. All right, all divided by radius squared, because we're trying to find the force of gravity between the ball and Mars, and vice versa, Mars and the ball. So that's our equation for force of gravity, and we want to set that equal to our net force, or mass times acceleration. And when we look at this, we kind of want to think, we have mass in our net force equation. We need to think which mass is going to be represented in that net force equation. So we're going to have to determine which object is actually has a noticeable acceleration. So when we drop that ball, does the ball have a noticeable acceleration, or does Mars have a noticeable acceleration? And our answer should be that the ball is the object with the noticeable acceleration. So that is the mass that we're going to use in that net force equation. Okay. So we're setting our force of gravity equal to that net force. And when we do mass times acceleration, we're using the mass of the ball because that is the object with the noticeable acceleration. And lucky enough, the mass of the ball or the mass of whatever object we are dropping cancels out. And that's good because we weren't given the mass of any other object. So that just leaves us with our constant times the mass of Mars all over our radius squared equal to acceleration. So then from here, we're able to just plug in what we know. We know g is always at 6.67 times 10 to the negative 11th. We know our mass of Mars is 6.4 times 10 to the 23rd kilograms. And we know our radius between the two objects is 3.4 times 10 to the 6th. And is radius squared, so we need to square that. And we should find the acceleration due to gravity on Mars is 3.7 meters per second squared. And we can just add down at the end because we know gravity always pulls an object downward. Okay. So that's another type of equation you'll see with these problems, okay? And again, what's cool is the force of gravity between that Mars is attracting the ball with, the ball is attracting Mars with that same force of gravity, but since the ball is so much smaller, that is the only object that we see accelerate, okay? Because yeah, if we look at that net force equation, as our mass goes down, acceleration goes up, okay? Whereas Mars is so massive that as the mass goes up, the acceleration goes down, that we're not really going to notice anything. Okay. Awesome. So just a couple things to kind of note about that equation before we end for the day. Oops. So if we look at this equation, we have our force of gravity is equal to constant times our two masses over r squared. Just some things to take note of. As always, make sure when you're doing your calculation, your masses are in kilograms. So don't be fooled when you're doing problems. If you see grams, make sure you convert that to kilograms. Okay. And vice versa, your radius needs to be in meters. Okay, so don't be fooled if you see kilometers, okay, you want to convert that into meters. And then if we look at this equation a little bit more, we're going to see that our force of gravity is directly related to our two masses. So what that means is that as the mass of the object goes up, your force of gravity is also going to increase. Okay? And if you kind of compare that to maybe like a cake, if you see a little cake versus a big cake, you're going to be much more attracted to the larger cake because, yeah, there's just more of it. It looks more appetizing. Yeah. The more the cake, the better it is. Whereas if we look at force of gravity and radius, we're going to see that we have that inverse square relationship. So that means as we get further away, as your radius increases, our force of gravity is also going to go down. And it's go down by a factor of r squared. Okay? And again, if we kind of think about that cake scenario, the further that cake is, the less pull you're going to feel towards it. You're like, oh, it's so far away. I don't really need it, whatever. But the closer that cake is, if you put it in front of yourself, it's going to be pretty hard to turn down. So just like with cake, the closer something is, the more attracted you're going to be to it. Yeah, they're just kind of hard to turn away. Okay. So those are kind of the highlights of universal gravitation. Please let us know if you guys have any questions, and we hope you have a great day.